It is an honor for me to present in this great research review and show our effort on exploring user authentication on voice assistant systems. I will introduce a voice assistant system that we are explore that is training free and can be integrated with current wearable and VA device to perform authentication. So about myself, I'm currently a PhD candidate at ECE under the supervision of Dr. Yin Chen. And I'm currently on the academic job market and searching for the faculty positions. My research interests mainly reside in cybersecurity, privacy, mobile sensing, healthcare, and IoT. And also I have many papers published in top tier venues such as CCS, Mobicom, and Mobisys. So in this talk, I want to introduce our recent work that leverage speech vibration captured by wearable device for user authentication. In recent years, smart devices such as Google Home and Amazon Echo have incorporated advanced speech recognition techniques that can enable device to understand natural language. By using voices as input, a user can smoothly and conveniently interact with their voice assistant systems using their voice command. Such a convenient functionality have been quickly adopted in various applications, such as playing music, shopping online, managing calendar events, and controlling smart home appliances, also making phone calls. The convenient usage of these applications made voice assistant systems widely deployed in home, workplace, and even public spaces. So with this growing trend, more and more people will tend to use a highly critical voice command to complete important tasks, such as storing credentials for accessing personal devices, making a significant amount of purchase through the user's associate account, or unlocking the front door of a house. The significant financial benefit of using such voice commands will lure the adversary into faking the user's comment to get a user's credential, making unauthorized purchase or control security critical IoT devices. For example, an adversary can get a user's credential for accessing personal device by asking, "Okay, Google, what is my password?" The adversary can also make a significant amount of purchase through the user's associate account by telling the VA system, Alexa, order a MacBook from Prime now. And depending on whether the adversary can launch the attack under the presence of the user or not, we summarize two potential attacks in two main categories. The first one is attack on user's absence. In this attack, the attacker can use his own voice to try to fool the VA systems. And for the impersonation attack, the attacker can try to mimic the tone, the speaking rate, and also the speech content to fool the VA device. Well, replay attacks is the attack that most accessible to the adversary, and it has drawn considerable public attention. The attacker will first record the user's voice commands through recording devices, and then replay the record voice command by using a digital playback device, such as a loudspeaker, to fool the VA device. Such attacks are very easy to launch, as a smartphone can be used as a digital recorder and playback device without attracting any attention. When the user is present, the attacker cannot launch the attack by directly talking to the VA device. However, he can launch imperceptible or inaudible voice commands. For example, the attacker can use hidden voice commands that leverage the position gap between human and learning-based speech recognition models, and generalize noise-like voice command that can be understood by the machine learning model, but not a subject to fool the VA systems. Such attack sound can even embed into the voice command into background music or even audio channel of the video stream to move a large number of VA systems remotely. The attacker can also launch a completely inaudible attack by mapping the record voice command into ultrasound frequency bands that cannot be perceived by human ears but can fool the VA's device. While the human ear cannot perceive the ultrasound voice command, the VA device microphone can map such voice command in the ultrasound frequency into a normal frequency band and understand by the underlying machine learning models. These attacks are perfect for spying. For example, an adversary can initiate an outgoing voice call for the eavesdropping attack, or injecting face information or post users sensitive information online. Existing authentication methods are mainly based on the microphone readings, based on acoustic features. Such methods solely relied on the microphone reading, and they can be vulnerable to many acoustic attacks, such as replay attack and hidden voice command attacks. To add another layer of defense, some VA systems explore a second factor to secure a voice comment, such as challenging questions via audio capture, replay messages, calls, or even a virtual button on the user's mobile devices. However, this approach usually requires significant user effort and can be prone to users' careless behaviors. Our group's earlier work, Voice Live, also demonstrates the potential of capturing unique vocal check information using dual microphone on a smartphone. However, such method requires the user to place the phone very close to the mouth to capture the vocal check characteristics, which is not applicable to voice assistant system that usually access from a long distance. So our idea is to use wearable device to capture aerial speech vibration to perform user authentication. The wearable devices are usually worn on user's body and rarely left unattended. It is natural for us to leverage such pervasive personal devices as trust tokens to facilitate voice command authentication. Our basic idea is to leverage wearable device accelerometer to harness the aerial speech vibration. The speech in the vibration domain involve unique time and frequency domain characteristics that help us to differentiate different users. And in addition, the vibration domain characteristics are very different from that in audio domain, and it is very difficult for an adversary to generate to spoof the vibration domain-based authentication. More importantly, the accelerometer usually have a very short response distance to sound, which is approximately 30 centimeters. That could effectively prevent the aforementioned acoustic attacks that usually launch from a far distance. To implement this basic idea, our goal is to develop a low-effort, training-free user authentication through cross-domain similarity. When a user gives a critical voice comment, our approach explored the accelerometer on the user's wearable device to capture aerial speech in the vibration domain. The same speech can also be captured in the audio domain via the VA device microphone. By comparing the vibration triggered by the aerial speech and also the audio recording of a voice comment recorded by the VA device microphone, we can perform a training-free authentication. Our system can be easily integrated with existing VA system and wearable device without making any hardware modification. The system is also a low effort and privacy preserving, as it does not require store any privacy sensitive voice templates, such as those used in the current Google Home and Amazon Alexa. More importantly, our system can provide enhanced security as it leverages the short response distance of the accelerometer to prevent various acoustic attacks. To enable a training-free authentication, a key challenge is that we need to compare the vibration signals captured by the accelerometer and the microphone readings. But there is a huge sampling rate difference between the signals in the audio and the vibration domains. To enable a training-free authentication, we derive a spectrogram mapping relationship between the aerial speech vibration and the audio speech, and convert the microphone data into a low-frequency accelerometer data to facilitate the cross-domain comparison. There will be a number of challenges to achieve such a cross-domain comparison. The first is that because the wearable accelerometer are designed to measure the movement of the human body, they have low sensitivity to the aerial speech vibration caused by human speeches. Second, the distinctive hardware design of the microphone and accelerometer make the sensor reading are very difficult to directly compare. Third, since we are using microphone and accelerometer from two separate devices, we need to ensure that both devices can trigger simultaneously to record the same voice command for comparison. Let's first take a look at the design of the accelerometer. The current accelerometers in wearable devices are MEMS sensors that have three components: an initial mass, spring legs, and stationary fingers. The initial mass is anchored to the substrate using two pairs of flexible spring legs. When an acceleration is applied, the initial mass will move and cause a change in the capacity between the stationary fingers. And such capacity changes will be measured as analog signal that reflect acceleration. When human speaks, the sound is measured as the subtle movement of the initial mass, and it can capture as an analog signal. In contrast, the microphones are also MEMS sensors, but differently. The microphone uses a pressure-sensitive diaphragm to capture the sound wave as analog signals, which are amplified and fed to a low-pass filter with a cutoff frequency about half of the sampling rate to remove the aliasing effect. An analog-to-digital converter is applied to digitize the analog signals. Differently, the accelerometer measures the sound wave in terms of the vibration of the initial mass. The accelerometer does not contain a low-pass filter, and it can capture the vibration signal approaching its sensing limit. It can be up to 4K Hertz for the smartwatch we are using. We first studied the sensitivity of the wearables accelerometer to live human speech. We use a smartwatch to record voice commands spoken by a live human with different sound pressure levels, and the distance between the subject's mouth and the smartphone is around 10 centimeters. We can observe that the wearable can capture speech vibration when the sound pressure level reaches 70 dB, and the amplitude grows with the sound pressure level. When the speech vibration reaches 80 dB, which is a presentation level volume, the accelerometer can clearly reveal the speech vibration. We also test the capacity of the wearable accelerometer on picking up voice under wear subject to wearable distance. We can find that under a distance of 30 centimeters, the response can be barely observed. And such a short response distance can help us to shield the system against various acoustic attacks. For the synchronization, we need to synchronize the microphone reading and accelerometer readings. We developed two types of methods based on the network condition. Our system will use the Wi-Fi communication-based method if the network delay is low, and the VA device detecting a wave word will send a triggering message through Wi-Fi to trigger the data collection on the wearable devices. And when the network delay cannot be ignored, the system will explore the accelerometer on the wearable device to detect the wave words in parallel with the VA device, which will trigger the data collection on both devices separately. Since the accelerometer reading will collect substantial noises that are caused by human motions, such as walking and hand tremor, for reliable user authentication, we adopt a high-pass butterworth filter to remove the impact of human motions and reveal the vibration for cross-domain comparisons. And after the data denoising, we develop a segmentation-based method to extract the accelerometer data containing the voice segment based on moving variance. Intuitively, the accelerometer data will experience high variance under the presence of human speech. And as we discussed previously, the accelerometer can capture up to 4K Hertz, 4K Hertz data, but usually the vendor of the wearable device will limit the sampling rate to below 200 Hertz to reduce the power consumption. Such a low sampling rate will cause a significant signal aliasing. According to the Nyquist theorem, any signal sampled at a frequency lower than half of its real frequency will cause the signal aliasing. We show an example for illustration. We play a drop signal of 500 Hertz to 1000 Hertz, where the accelerometer are sampled at a frequency of 100 Hertz. We can see that the microphone data, they can clearly capture the drop signal, but for the accelerometer, it will capture as a zigzag curve. which means multiple frequencies are mapped to the same frequency due to the aliasing effect. To enable cross-domain comparison under such significant aliasing, we convert a feature in the audio domain into vibration domain by modeling such aliasing effect. We first compute a spectrogram of the audio signals that represent the signal's energy distribution over range of frequency in short time frames. Next, we convert the audio spectrogram into the vibration domain by using the aliasing formulation as we discussed in the previous slides. And after this domain conversion, we can compare the spectrogram in the vibration domain with the aliasing spectrogram in the audio domain. We develop normalization methods and calculate the 2D correlations, which can reflect the similarity of these two types of signals for user authentication. If the correlation is high enough, our system will authenticate the user. Otherwise, our system will reject the voice comments. So let's put everything together. We summarize our system overview. When a wake word is detected by the VA systems, the VA system will perform a cross-domain synchronization to ensure the wearable and VA device start the data collection simultaneously. And depending on the network condition, we design two types of synchronization methods. Our system then removes the noises and extracts spectrogram of the voice segments. To adjust the huge sampling rate gap between the microphone and accelerometer, we propose a feature domain conversion, which converts the spectrogram in the audio domain into low-frequency aliasing representative. They are comparable with the signal in the vibration domain. To adjust the residue offset, we propose a 2D serial correlation, which quantifies the cross-domain similarity between the audio and vibration spectrograms. If the 2D correlation is over a predefined threshold, our system will verify the voice comments. And we evaluate our system using two types of smartwatch with different sampling rates. In the experiment, we asked the participants to wear the wearable device and speak a set of representative voice comments, as we show in this table. And the sound pressure level is around 80 dB, which is a typical presentation level volume. We involve 10 participants to test our system, and the speaker will speak 20 representative critical voice comments. We also collect data of 10 hidden voice comments to evaluate our system's robustness against hidden voice attack. So we first evaluate our system under normal situation when the attacker does not present. We can find that our system can achieve a very high 99% true positive rate with close to 0% false positive rate for both smartwatches. And under random attacks and replay attacks, the area under the curve is around 90% for both smartwatches, showing that our system can defend these two types of attacks. And under the hidden voice comment attack, we compare the cross-domain similarity recorded from the two devices for hidden voice attack and also human voice. We can find that the hidden voice comments have very low correlation score. This makes our system can differentiate the hidden voice and human voice based on their cross-domain similarity. We also evaluate the robustness under ultrasound attacks. The ultrasound attack is to modulate users' voice comment into inaudible frequency range, and then which can be demodulated by the microphone. We play a chirp signals, ultrasound chirp signals across 15 kHz to 25 kHz. And then we can find that for the VA microphones, it will clearly record the audio signal. It can clearly record the audio signal of the ultrasound. While for the true wearable device, the accelerometer will not respond to the ultrasound signals, showing that it can defend against inaudible attacks. So in conclusion, in this work, we study wearable assist training-free user authentication by using the wearable device. We explore the wearable device motion sensor to harness aerial speech vibrations to verify the highly critical voice comments. Furthermore, we develop a cross-domain comparison scheme to enable training-free and privacy authentication. Finally, we demonstrate the effectiveness and robustness of our system against both various types of acoustic attacks through extensive experiments. So that's all. That's all for my presentation. And please let me know if you have any questions. Thank you.